So this is a riff on the easiest problem in projectile motion, but it's slightly different. We have a cannon that fires a ball off a cliff that hits the ground a known distance away. We want to know the speed of the cannonball and how fast it's going when it hits the ground. Say to yourself, self, there is only one equation in the x direction, and write it down. We don't know time, so we'll have to switch to the y direction to find that. dy equals 1/2 gt squared, so t equals 2 dy over g square rooted. Then plug in to get 3.5 seconds. Now plug that into Vx equals dx over t and you'll get 371 meters per second. How fast it's going when it hits the ground is the vector sum of the x and y components, so we need to find Vy. That's as easy as v equals v0 plus at, which is 34.3 meters per second, negative meaning it's downward. Add these velocity vectors tip to tail, and the Pythagorean theorem rounds to 373 meters per second. This next problem is asymmetric. We have a cannonball fired at an angle from on top of a cliff, and we want to know how high it gets from the ground, how far it goes, and how long it took. It's probably easiest to treat this as two separate problems, one on the way up and one on the way down. And of course, the first bit of math is to separate the initial velocity into x and y components. As we've done many times, solve the definition of acceleration for time up. You'll get 3.06 seconds. Note that this problem is not symmetric, so you can't just double this to get the total time. We'll figure out time down later. Meanwhile, we can use the distance formula in the y direction to find that the height from the ground is 106 meters at its highest point. This now reduces the second half of the problem to the easiest projectile motion problem. What if you have an object that is fired at 51.96 meters per second from a height of 106 meters? Solve the distance formula in the y direction to find the time down. Add time up and time down to get the total time. And then say to yourself, self, there is only one equation in the x direction, and use it. We're done. In this next problem, a cannon fires a ball at an angle, but it hits a tree 4 seconds later. We want to know its initial speed, we want to know how high up it hit, and we want to know if that answer makes sense. We can't separate the initial speed into x and y components because we don't know the initial speed. So let's start in the x direction and say, hey, Vx equals x over t is our only equation. 450 meters in 4 seconds gives us 112.5 meters per second. Now we can use Vx equals v0 cosine theta, only this time we're solving for v0. Plug in your numbers and you'll get 130 meters per second. Now that we know v0, we can find the y component of the velocity to be 65 meters per second. And because we already know the time, we can use the distance formula to find the height. We get 182 meters. A quick Google search tells us that the tallest tree in the world is Hyperion, a sequoia, and it is 115.7 meters tall. So our answer doesn't make sense, and this question is not terribly realistic. This next problem is one of those ones where you would be asked to write the equations but not solve them. A golf ball cannon fires a ball from a cliff but up a slope. The question is, how far away does it hit the ground and how long is it in the air? Or more precisely, what equations would allow us to figure that out if we solved them? We can of course start by finding our vector components. Then say to ourselves, self, there is only one equation in the x direction. Unfortunately, this equation gives us two unknowns. In the y direction, we've got the distance formula, but that gives us the same unknown of time plus an additional unknown of y. So we need more equations. The good news is, x and y are the sides of a triangle that we know the angle of. So our last two equations come from trigonometry. Tangent of phi equals y over x. That doesn't give us any new unknowns, so we have as many equations as we have unknowns. Hooray! Finally, to get the distance up the slope, we could use sine or cosine.